We're now going to talk about the resolution of an experiment. So there are several resolutions we're going to talk about. Resolution 3, I imagine there's resolution 1 and 2 that we just totally don't talk about at all, but a resolution 3 design is one, I'm going to define it first, then I'll give you an example, is where the main effects are aliased. So if you remember when we set C equal to AB, right, that was aliasing C with a two-factor interaction AB. So resolution 3 is when a main effect is aliased with a two-factor interaction, which I'm going to abbreviate as two-factor interaction. Okay? And then the main effect is not aliased with any other main effect. Okay, so A, B, C are completely, you can distinguish each of those, but the main effect might be aliased with a two-factor interaction. Right? I think that was the example we did before. Resolution 4, right, is where no main effect is aliased with any main effect or two-factor interaction, right? But two-factor interaction aliased with other two-factor interactions. And then the last one we're going to discuss today is 5. And resolution 5 is no main effect or two-factor interaction is aliased with any main effect or two-factor interaction. Okay, so I'll give you an example of how we might do this, right? So if we take a factorial experiment with 3 factors like we did before, right, then, hey, that's resolution 5, everything's good, right? But if I fractionate it, right, and I take -1, meaning I'm going to run half the experiments. So now there's really only 2 to the 2, or 4 experiments, and it's separated as I did before. That, as you recall, is of resolution 3. So do you see how we write the notation? 2 is telling us how many levels. This is how many factors we have. This is how much we fractionated or how clever our subset is. And then this describes the resolution of the final experiment, meaning I can now know that I can get I can identify main effects, but some of those main effects are aliased with a two-factor interaction, so my ability to know what's what in this experimental design is a little bit compromised. What I'm going to show you next is if I have a 4-factor design and I fractionate it in half, right? So I take a clever subset, this will be resolution 4, meaning that all of those main effects are clear. I can estimate what main effects are significant, but some of the two-factor interactions are confounded with other two-factor interactions. So what I'm hoping is that only like 1 or 2 of those main effects are actually going to be significant, and then I do not have to consider the other 2, and I can be done with half the number of experiments that I've done. So let's look and see what this looks like. If I'm going to design this experiment, well, what I would do is I would have A, B, C, and I am going to deliberately confound factor D to equal A, B, C. And so the way I'm going to map that out is I'll start here with A. How many rows do I need to include? Well, how many experiments are there going to be? 2. 4 minus 1 is 3, so 2 to the 3rd power is 8. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 experiments are what I'm going to have to run. So I would like you to pause the video and try and complete the rest of the table to include what this column would look like. I'm assuming you've paused the video and you've now returned, so now we're going to complete the table. So B is going to be minus minus, and then C. Now notice that there is half the experiments where A is at the high, A is at the low. Half the experiments B is at the high, B is at the low. Half the experiments C is at the high, C is at the low. So when we go to D, that's going to be the multiplication of A, B, and C. So a negative and a negative is positive, and a negative is a negative. Odd number is a negative. So this is positive, positive, negative, positive, negative, negative, positive. Now let's look. 1, 2, 3, 4 positives, 4 negatives. So half the experiments have D at the high positive, half the experiments have D at the negative. This is now 8 experiments, not 16 for 4. And so you're able to run these 8, and if everything is significant, then you need to run the other half. But if only a subset are significant, then you can go ahead and estimate those interaction effects, much like we did before, and then you can drop the ones that are not significant, and your experiment is done. There are some other designs that go beyond the scope of what we're going to talk about. So I'll just write a couple of them down here that are out of scope. So sometimes there are 3-level. That's oftentimes done when you have categorical variables that are not continuous, so you can't break them into a high and a low. You might have to have like 3 different types of shoes for the run. Well, you can't really do anything different with that. That's categorical. Or sometimes people find efficiencies in creating 3 different levels, and they do cubic designs is what they call them. There's mixed level, and that's where some variables are going to have multiple levels, like 5 levels, like the explosive design one that I told you about. I think we had something like a dozen different static mixers, which was categorical. So for each level of the static mixer, it's almost like you had to rerun the other combinations of the experiment to see how they perform. Right, so mixed level, and then Latin squares. And the reason why I bring those up is, these are more advanced topics, and I just want to make you aware that there is a whole world of experimental design that can go quite deep, and you can have an entire course on experimental design, and beyond that, you can start looking at response surface optimization, which goes even further. We're just giving you an introduction so that you can use it to get some efficiency when you're designing your experiments. Okay. Let's talk about one other thing that you have, right? So we talked about nuisance factors, right? Or these noise variables. They're things that happen in your thing that aren't something you're really interested in, but they're just things that happen in the environment. So with neural imaging studies, for example, ambient light can be a nuisance variable. It can affect the readings. It can affect the magnitude of the readings, yet it's not what you're interested in. You don't care whether the light affects people's cognition. What you care about is whether it's messing up and harming your data. So if I look at nuisance factors, sometimes the nuisance factors are unknown and uncontrollable. Right? I can't control them, and I don't even know that they exist. Other times, the factors are known, but I can't control them. They're uncontrollable. And sometimes they're known and controllable. And so what do? Well, if they're unknown and uncontrollable, this is why we do randomization. And so what I will typically do in an experimental design is I will put an experiment order, 1, 2, 3, right, all the way down to 8. That is my experiment order. And then what I'm going to do is I'm going to then randomize the order of these, right, with like a random number generator, and that will be my order, right? So I'll call that my order, which might be a different order than my experimental design. And in doing so, that allows me to shuffle them up, but I can still reconstruct what combination of variables I was going for when I designed my experiment. And so randomization is basically trying to average over the effects of any of these unknown or uncontrollable factors. If we have known but uncontrollable, so I can't really do anything about it, but I know that it's a variable. So for example, I can't control the order of gender order of people coming into a clinic when I'm doing medical trials, right? Or I can't necessarily control the age. Or in my running example, I can't control the temperature, right? Because the temperature is just whatever the weather is. And I know that it's a variable, I can measure it, I just can't set the temperature if I'm running outside. So we use this method called analysis of covariance. And so basically what you're doing is you're measuring it, you're throwing in the regression model, you're looking to see if the order effect has any impact on what you're doing. And then if it's known and controllable, we do this thing called blocking, which is where we're going to say, okay, I want to have this randomized order that is of like 24 subjects, and I can run 6 subjects a day in my neural experiment. Well, that means that I'm going to have 4 days of 6 subjects. So I might put a little bit more thought into which 6 experiments do I do so that I don't end up being day 1 and 2 are all at A at the high, and day 3 and 4 are all when A is at the low, and then I may not be able to control for, was it the day of the week or factor A that had an impact, right? So I might want to put a little bit more thought into how I divide up the experiments across those blocks and then randomize within the blocks for doing that. That's called blocking. We're not going to go into any more detail than that other than to let you know that it's a thing. It's out there, and it's something that you might want to consider if you're doing more experiments.